All right, in this video, we are going to talk about the acid ionization constant, also known as Ka. So when we are dealing with acids, that is when we are going to deal with Ka. That's what the little A means. So we've talked about Kw, which is water. We're talking about Ka in this video, which is acid. In another video, we're going to talk about Kb, which stands for basis. And then we've already talked about Kc, which is basically any regular equilibrium equation that isn't an acid, a base, or water. So if we think about a general equation for water, or not water, sorry, for an acid, we are taking our weak acid, right? We're dealing with weak species because we're calculating equilibrium constants. We only have equilibrium constant for weak species. So we have a weak monoprotic acid. We combine it with water. We're going to transfer that proton over. We're going to make an A- and an H3O+, right? So remember, liquids don't get included in our equilibrium expression. So our kind of generic expression for acids is going to be the hydronium times the A- divided by the HA, right? Obviously, just like we talked about in the last unit, when we're actually writing out our Kas, we do want to be specific to the equation that we have. We don't want to use that A and HA. We want to use the actual chemical species. So let's look at an example. So what is the ionization equation for carbonic acid, and what is the Ka if the initial concentration of acid is 0.975 molar and the equilibrium concentration of hydronium is 6.8 times 10 to the negative 4? So we are going to start with, change my fonts for a second here. All right, so we're going to start with carbonic acid, which is H2CO3. Okay, so even though this is a polyprotic acid, right, it has two H's, whenever we're doing K calculations, we're only ever going to take the first hydrogen off. We're never going to do multiple steps because there are different Ks between the first one and the second one. Okay, so we're going to combine with water. Shift that over a bit so I can actually make my ice table. And then this, it's going to be in equilibrium with the products, which are going to be the hydronium and the HCO3 minus. Okay, so we're going to make our ice table. So we are going to have our initial, our change, and our equilibrium. Oh, hold on, someone's yelling. Okay, so once we have our ice table set up, the next thing we're going to do is we are going to completely X the water out of our table. And the reason we're going to do that is it's a liquid. It doesn't belong in our ice table. It's not going to change. Okay, so we have the initial concentration of acid as 0.975. Initial concentration, excuse me, of hydronium, we're going to assume is 0. And same for the HCO3 minus, right? Change values, minus X, plus X, and plus X. Okay, so that means our equilibrium concentration of H2CO3 is going to be 0.975 minus X, and the hydronium is just going to be X, and the HCO3 minus is also just going to be X. Okay, next thing we want to do, and you're going to find that we do this a lot more in this unit than we did in the last, is that a prox check. You're going to find that a lot of these questions are going to have pretty small Ks. So we definitely do want to do our prox checks. So we're going to do the initial, so 0.975 divided by K, so that's 6.8 times 10 to the negative 4. This gives me 1,433. So it is greater than 1,000, so I can approximate. Remember, we said that when we can approximate, that means for our reactants and our reactants only, so in that case, just the H2CO3, we get to get rid of that minus X, okay? So now that we've done that, we can set up our equilibrium law expression. So we're going to have that Ka is equal to the concentration of hydronium times the concentration of the HCO3 minus, and that is going to be divided by the concentration of that H2CO3. Okay, so what do we have? We have our Ka. We know that it's 6.80 times 10 to the negative 4, and that is going to equal x times x, right? Or we can write it as x squared, right? And x times x, because hydronium is x and HCO3 minus is also x. Then we are going to divide by the concentration of H2CO3, which is 0.975. Okay, so from here, it's probably one of the most straightforward K calculations to solve. We're just going to take this 6.8 times 10 to the negative 4. We are going to multiply it by the 0.975. Going to get our answer, and then we're going to square root it because it's an x squared. Okay, so we come up, I don't think I typed something in right. Maybe I did. Hold on. No, I was right. I got the right number. It seemed bigger than I was expecting it to be. So x is going to be 0.0257, and that keeps going. Okay, so from here, what did the question ask? What's the ionization equation, and what is the equilibrium concentration of hydronium? So we've just calculated x. X does represent the equilibrium concentration. Significant digits, we can go to 3. So we are going to wind up with the concentration of the hydronium as 0.0257 moles per liter. Okay, so if you didn't recognize that you could have done that and you chose to graph it instead, and you did the x squared over 0.975 minus x, you get a super similar answer. You get 0.0254. So it's just that last digit that's going to be a little bit different. So that's where I was saying it is helpful to recognize when you should approximate, because on the diploma, they will approximate. They won't not approximate, okay? But if it's a unit test and you don't recognize that you could have approximated and it's like a written response, I will still give you the full marks, okay? Just be aware that if it is a multiple choice, you're going to find that your answer isn't going to be a perfect match to what they have because they approximated and you did not, okay? So just do be aware of that if you find that you are not doing approx checks on your questions, okay? So most questions like this actually aren't going to ask you for the hydronium. They're actually going to ask you for the pH, right? So it would just be that additional step once you've determined what X is, because X is the hydronium, to just do the negative log of the hydronium and obtain your pH from there. Okay, that's definitely, I would say, the more common form of seeing these questions. Okay, so we also see that we sometimes see questions that go the other way, right? If you think back to when we did equilibrium the first time, there were some questions where we had to use K to solve for X. And then there were some questions where we were able to figure out what X was because it already gave us the equilibrium concentrations. So in this case, it says a 0.25 mole per liter solution of weak acid HA has a pH of 3.50. What is the Ka for this acid? So pretty common to be dealing with unknown acids in Chem 30. Often we use HA or HX to be our unknown acid. So we're going to have the HA plus the water. This is going to be in equilibrium with our hydronium. And that A minus. There we go. Okay, so same deal, ice table. One of my children is making crazy bird noises. So from your ice table that you've now set up, same deal, we're going to get rid of the water. So we have an initial concentration for the unknown. It's 0.25. Okay, we're going to assume these start at 0 because the question doesn't tell us otherwise. So our change values, we're going to have minus x, plus x, and then plus x. Okay, so at equilibrium, we're going to have the 0.25 minus x, and then these guys over here are both going to be x. So this question gave us the pH, right? It told us the pH was 3.5. So if we think about what we can get from pH, we can get the hydronium, right? If you think about your pH equations, we talked about the concentration of hydronium is equal to 10 to the negative pH. So I know that X has to equal 10 to the negative 3.5. Okay, I find personally, I tend to leave X as 10 to the negative 3.5 when I sub it in. Because if you actually do 10 to the negative 3.5, I want to say you get a gross number. Let's see. Oh, I didn't do that right. Got the negative. There we go. Yeah, you get like 3.16227766 times 10 to the negative 4. So I tend to just leave it as that. So I tend to write this as 10 to negative 3.5. And then I say that this one over here is also 10 to the negative 3.5. Missing point, there we go. And then I say over here, this is 0.25 minus 10 to the negative 3.5. Okay, so now we set up our Ka expression. So we get that Ka is equal to the concentration of hydronium times the concentration of A minus. And that's all going to be divided by the concentration of that HA. Okay, we're trying to solve for Ka, so this is going to equal our 10 to the negative 3.5. And I'm just going to square that so I don't have to write it twice. Okay, although this bracket is wonky. There we go. Okay, and that is all going to be divided by our HA, which is 0.25 minus 10 to the negative 3.5. Okay, so I don't want to say a trick, it's not a trick, it's just how I tend to enter this on my calculator because I just find it easier, is I do 10 to the negative 3.5 and I say equals, so that then becomes my answer button, and then it's a little bit easier. Instead of me having to type 10 to the negative 3.5 a bunch of times, I just have to do it once. So I do that, I get my answer, and that's answer is representing, you can't see what I'm pointing at as I sit here pointing at my computer, it is representing 10 to the negative 3.5. So that I do my answer squared, because it's 10 to the negative 3.5 squared, then I divide by, and then in brackets 0.25, minus my answer. Okay, so it looks kind of like, oh, wrong way. There we go, right? So I got the 10 to the negative 3.5 so that I could program that as my answer, and then I did answer squared divided by the 0.25 minus the answer. You don't have to do it that way. You can definitely enter 10 to the negative 3.5 each time if you want. I don't want to say lazy, but I guess I'm going to say I'm lazy and I don't want to enter it a million times, so I just enter it once so that I can use the answer button, because in my mind, that's easier. So what do I get as my Ka? I get 4.0, or I guess, oh no, it had 5 zeros, so yeah, 4.0 times 10 to the negative 7. Okay, this is a number we expect. We are going to expect that for the majority of our weak acids and weak bases that we are going to have Ks less than 1. Okay, if our K is considered greater than 1, usually we consider that to be a strong acid or a strong base, okay? So, same type of calculations we did in the last unit. Really the only difference is might give you a pH or it might ask you for a pH. So it's just kind of tacking on that extra step at either the beginning or the end of the question. Okay, so here's another example for you to try. So what is the pH of a 0.1 molar solution of nitrous acid? Right, so nitrous acid is HNO2, AQ, combining it with water. Okay, and that is going to give us our hydronium. And that nitrite ion. Okay, so ice table, ICE. We are canceling out the water. Okay, initial concentration we have for the HNO2 is 0.10. This is 0. This is 0. So why am I doing an ice table and not doing stoic? Because sometimes when you guys see a question like this, you're like, sweet, I'm going to just write an ionization equation, I'm going to do some stoic, and I'm going to plug that in. So the reason we can't do stoic is nitrous acid is not a strong acid, right? If it's one of the 6 strong acids, I can do stoic. But if it's not a strong acid, I'm going to have to create an ice table, okay? So that's why I'm making an ice table and I'm not just doing my ratio and then my calculation. So change values, minus x, plus x, and then plus x. Okay, so equilibrium, we're going to have 0.10 minus x, and then we're going to have x and x. Okay, so remember in the first example we did, we said, oh, we better make sure that we go do an approx check, so let's do that as well. So HNO2. Hopefully the number in this really old data booklet is still the same number that you guys have. If it isn't, then let's just pretend that the number I'm about to use is the number that you have as well. So in this particular case, the question didn't give me the Ka, but that's okay because I have my data booklet and I can go to my data booklet and I can find the Ka. So if you find the nitrous acid, right, so I just Googled your data booklet. I figured that would probably be easier. Of course, it is now sideways though, because this table is sideways. But here is your nitrous acid. So it's on the top half of the page, just a little bit above the staples. So HNO2 turned to NO2 minus. It has a Ka value of 5.6 times 10 to the negative 4. So I'm glad I looked it up because it has changed from 25 years ago. Okay, so what did I just say? I already lost the number. 5.6 times 10 to the negative 4. So when we go to do our Ka, or not our prox, oh my gosh, I can't talk. When we go to do our prox check, we're going to take our initial, which is 0.1. We're going to divide by the K, which was 5.6 times 10 to the negative 4. We get 178. So unfortunately, there is going to be no approxing in this question. We are going to have to leave all of those x's in, okay? So we're going to have that the Ka is equal to the concentration of hydronium times the concentration of the nitrite. And that's going to be over the concentration of the nitrous acid. Okay, so within here, we're going to have the K, which was 5.6 times 10 to the negative 4, and that is going to equal our x squared over our 0.10 minus x. Okay, so a question like this, probably the simplest way to solve this is just to graph it. So go into your graphing, set y1, it's x squared divided by, in brackets, 0.1 minus x. And then set y2 as 5.6 times 10 to the negative 4. Have your calculator graph it for you. And then have your calculator tell you what the intersect is. So we come up with x is equal to 0.007208, and that number keeps going, okay? So what did it ask me for? It asked me for the pH. So I solved for x, which also represents the concentration of hydronium. So to solve for the pH, we can just do the negative log of our x value. Okay, so in our calculator, we're going to do negative log answer, or I guess it's potentially not your answer, but you know what I mean. So take that number. So negative log 0.0072085, and that number keeps going. And we're going to come up with a pH of 2.14. I want to say we can have 2 significant digits. Yeah, so 2 numbers out to the decimal place. Okay, so couldn't approximate. K wasn't quite small enough, which is why we had to graph. Previous example, we were able to approximate and we were able to get rid of the x. Okay, you're going to find most questions you can approximate and get rid of the x, but there are definitely some, like this particular example, where you're not going to be able to. So don't assume that you can always approximate. Definitely best practice is to check to see if you can or not.